Okay, I want to talk about two things. One is the modeling of district heating networks, and the second thing is how to include multi-objective targets when you do optimization for district heating networks. And this is from an ongoing project with our industry partner BEW, Berliner Energie und Wärme. This is the district heating provider of Berlin. Okay, so what is the motivation? Why do we want to look at district heating networks? If we want to have an energy transition in general, we cannot only look at the transformation of the power system, but should include the heating sector as well. But a lot of progress was made in the power section already. So now we should focus more on the heating sector. And for example, in Berlin, you have several technologies how to get your heating into your household. And one of them is district heating. And if you don't know what district heating is, in Germany, it's called Fernwärme. This is heat that is generated somewhere and then transported via pipelines to the households. In Berlin, it has a share of 33% of the heating in Berlin. If you look at this map, this is the blue part is the main connected grid. And so this can play a significant role when we want to decarbonize the heating sector. Okay, our industry partner BEW has a plan how to do it, a roadmap. They want to achieve 100% fossil-free fuel generation by 2040, but they are not sure how to achieve this goal because there are several technologies they could invest in. So this is where this project came to be. And the goal now is to explore different transformation pathways for this district heating network. So by different pathways, I mean is how can we get to this goal? What should we invest in to get to this goal? And the pathways should have reasonable trade-offs between costs and environmental goals. And in general, we want to achieve long-term investment planning for general district heating provider of urban areas, and especially for BEW because this is our industry partner for this project. Okay, so when we want a district heating network, we can look at it the following way. We can define it as a set of heating generation and transportation system, like a network. And this heat generation technologies could be heating stations that just produce heat from fuel, or there are some combined heat and power plants that produce heat and power at the same time, or different other technologies. And the main goal is to fulfill a heat demand. We can furthermore store heat if we cannot produce too much energy. And to make the whole system feasible, we even have a heat import, but we don't want to use heat import. Then we integrated the relevant markets. That is, for example, a fuel market. That is, we can purchase fuel for a given price to operate our heating plants. And then we have the power trading, where we either can sell the produced power from the combined heat and power plants, or we can buy power because of some of the technologies need power to be operated. And for all of that, we got as input demand and price forecast time series from our industry partner. Okay, now I want to show you what I want to optimize there. There are two things. The first thing is the operation optimization. And you can look at this example. We have here 3 different heating stations that take different kind of fuels and produce heat to fulfill a given demand. But now the question is, which of the stations should be operated? How much should they be operated? I mean, should they be operated at their full capacity or only part of it? And where is the energy flowing in all this, this network. So if we talk about operation optimization, we can model it as a so-called unit commitment problem. There are three decisions to be made that are the one I just mentioned, the commitment decision, which is here marked like this on and off, which one is operated. The production decision is how much are they operated, how much of the capacity. I just wrote here a percentage for visualization. And the network flow decision on which arc is flowing how much heat, power, whatever resource you just have. Yeah, and now you can put this in a mixed integer program. And I marked here there are several variables you can consider. I marked the one that I want to talk about. And the first one is this operation variable that is a binary variable and yeah, models if the unit is operated at a specific time. This is the commitment decision. And the second is the incoming and outgoing flow of units. This could be interpreted as this flow decision, but even at the same time as a production decision, because if you know how much heat is flowing out of a node, you know how much of the capacity is produced by this plant. Okay, and I want to optimize costs, the operation costs that are costs especially coming from fuel purchase and some activation costs of some plants. Okay, and now I try to put all of the constraints that are needed into this mixed integer program. And the basic constraint is the resource balancing or demand fulfillment. I have here a given demand, and I think that everything that I purchase of a given resource and that is flowing out of my nodes, of my storage and generation nodes, should be equal to the demand and everything that is coming in of a resource and is exported. So there should just be a balance. Then the second constraint is a resource conversion. And by that I mean that if I have a node where some resource is flowing in, then I have a function that transforms the first resource in another resource. For example, you have some fuel coming into a node and it's a heating station, then this function will transform it into heat. But this function we looked at as a piecewise linear function. Then we have some technical constraints. I briefly want to say what they're about. One is modeling some activation of units because there are some additional nodes or something is activated at a specific time point. And then you can use this activation to model, for example, minimum up and down times of generation units. And we include our ramping. That means that a unit can, or the change of produced heat in a unit cannot be too fast at one time step. There's like a limit how fast this could change. And the last things we look at is the storage management that, this and the other constraints here and technical constraints combine different time steps. For example, here in the heat storage, if you want to compute the level of a storage at a given time step, you need to know what was the previous level by some loss, because there's an efficiency of the storage, and what is coming in and what is going out of the storage. So you need to cover the time steps. Okay, and now I want to look at another thing. The first thing was operation optimization, but we are really interested in design optimization, or this is called sometimes investment planning. And therefore, I added here in our example another heating station. And the decision now for design optimization is, should I build this new heating station or not? So this is the decision I have to make. But then if I look at the previous problem, I have now this new option, which I maybe invested in. And if I invest in this, I can use this as well. So everything that I had in my solution of the previous optimization would maybe change, because I can now use this other heating plant. That's why I want to combine both of them in one mixed integer problem, because they are depending on each other. So the only thing I now change is that I add this variable that is a decision variable if I want to invest in a specific unit. And I add to my cost function the investment cost. And in my constraints, I only add this one, the investment decision. That is, if I have a unit that I invest in, then it can only be operated if we invest in it and not be operated if we do not build it. Yes, so I have all of them together, but now I think this is, I mean, we can solve this problem, but in reality, you do not have one objective, but several. So we included more objectives. The first is still the cost. The second is the emission of the system, like CO2 emissions. And the third one is the CHP heat. And by that, I mean the heat that is coming out of a combined heat and power plant. That is a plant that is generating heat and power at the same time. So we see this as a kind of efficiency factor. Okay, we heard a lot of times about multi-objective optimization mentioned in some of the talks, but I think it was never explained in detail, so I want to recall everything that you know what we're talking about. For multi-objective optimization, the problem is that we do not have one optimal solution, but several optimal solutions. And to know which one is optimal, we have this notion of domination. That is, if we have k different objective functions and a minimization problem, and we have two feasible solutions, x1 and x2, then x1 dominates x2 if the corresponding objective values for each of the objectives is smaller for x1 than, or smaller or equal than x2, and there's at least one objective function where the value is strongly smaller, then it dominates the other. The second notion we need is Pareto-optimal. A solution is called Pareto-optimal if there is no such other solution that dominates our solution. And the set of Pareto-optimal solutions is called the Pareto front. Here's a picture where you have the whole feasible region for two objectives, F1 and F2. I mean, if we can get both optimal, this is called the utopia point, but this is almost never possible because they are always, well, most of the time, conflicting. And there's in blue here the Pareto front, that would be the options that are Pareto-optimal. Okay, so most of the time we're not able to generate the whole Pareto front, or we don't want to do it because it is too large. Then we have to get a relevant subset of this Pareto front. And how we can do this is that there are several options, but in all of them, I have to combine my different objectives into one objective somehow. I will tell you how we can do this, but you have to do this such that your solver can deal with it. Yeah. Here's a brief overview of the different multi-objective approaches. They're very classical, basic version. The first is weighted sum. This is the one that Jaap used before, and I think it was mentioned in another talk as well. Where you have, for example, 3 objectives, and then you take a weight vector. I say you should take one that add up to 1, just to get a better overview, and then because then you can see them as percentages. And then you can combine the 3 objectives into one by a convex combination of objectives. The second approach you can use is similar because you take another vector, but this time it's not a weight vector, but it's called usually epsilon vector, because this method is called epsilon constraint method, where you decide to optimize for one objective and put some epsilon constraints on the other objectives. Yeah, and yeah, the third method is lexicographic optimization. There you have, similar to epsilon constraint, decide which is the most important objective. You have to give them an order. Here I decided for F1 to be most important and F3 to be least important. And then I first optimize for the first objective. Then I take this optimal value and put it as a constraint to the first objective and optimize for the second objective, get the optimal value, and then put it again as a constraint for the, or bound for the second objective and optimize for the third. The problem is you only get one solution by this. For each of the vectors you get in the other both approaches, again, just one solution, but here you can just make a whole sample of vectors to get several solutions, hopefully different solutions. Yeah, here's another overview over the different approaches. I want to compare them. Okay, how many solutions can I get for the weighted sum and epsilon constraint? It's just the number of vectors I sample. Then for the lexicographic optimization, it's just one. So, but most of the time we're not interested in how many solutions we can generate, but how many of them are really on non-dominated. So in the lexicographic optimization, okay, I just get this one solution, but for the others, I really have to filter them for non-domination, and this will reduce them immensely. Especially in the weighted sum approach, you sometimes generate, I don't know, 1,000 solutions, and then they end up just to be 3 different. Because, for example, the objectives are really scaled in different order of magnitude. And for the placement of the solutions, here's the difference between the weighted sum and the epsilon constraint. The weighted sum approach only gives you solutions on the convex hull of the Pareto front. If you again look at the definition, I even said this is a convex combination of the objectives, so you only get the solutions on the convex hull. But the epsilon constraint algorithm can give you even solutions that are on the non-convex areas of the Pareto front. And for the number of optimization calls, you have as many optimization calls as samples for the first 2 algorithms, and for the lexicographic algorithm, you have optimization calls for each of the objectives. So yeah, in total, I tried to summarize what I think about all the 3 approaches. And the first one is just often used in practice. Sometimes it helps you to get a brief overview what is going on. Sometimes it's really not beneficial at all, but it's used very often because it's simple. The epsilon constraint algorithm often gives the best solutions, but there's a lot of computational effort. And the lexicographic optimization is just good if you just want one solution and you really know which one of the objectives is the best. And I want to focus on those 2 because the weighted sum is used so often either way. I don't want to look at it again. So I want to use the epsilon constraint and the lexicographic optimization and change them a little bit and try to combine them. And I want to show you what we got out of it. And we want to see what it's good for our problem. Okay, yeah, I start with, because the whole problem is a little bit, huge. I start with 2 objectives. And I start with design and operation optimization, the integrated MIP that I showed you before. This is the normal lexicographic optimization, and I changed it the following way to get more than one solution. We just iteratively relax objective 1. That is, we got this P, which you can see as a percentage, how much I want to relax my first objective. So I get 1, 2, 3, 4, 5, 6, 7 different solutions. And I want to do this to have like a simple approach, but still get an overview of the Pareto front. And I tested this on an instance of the Berlin district heating network. This instance involves several different heating technologies. Most of them are typical gas heating plants. And I have 38 potential investments. I look over 25 years with a 24-hour time step. And here's like an overview how the basic structure is of it, but in reality, the graph is way bigger. The graph has about 2.9 thousand nodes and 3.8 thousand edges. And if we put all of it in the mixed integer program I showed you before, we have about 3.6 million variables and 3.5 million constraints. So it's huge. Yeah, again, as a reminder, we look at both operation and design optimization. We look for two objectives, and we use this lexicographic optimization with iterative relaxation. And this is what I got out of it. I think it's interesting to see the trade-off between the costs and the CO2 emissions that I get from the different solutions. I can see how many investments are taken in the different solutions. And what I found most interesting is that for the first three solutions, I have exactly the same investment, not only the number, but really the same investments. So from this, you can see that you can achieve a lot already if you only optimize your operational decisions without investing in anything. And the second thing you can see from this is the investments that really were taken. Some of them were not chosen at all. Some of them are chosen in all of the scenarios. So I would say they are robust investments. A decision maker should invest in all of them. And then there are some investments that are dependent on the cost relaxation. So we call them target dependent investments. Yeah, so in summary for this approach, I see I can with small effort get a nice overview which of the investments I should take definitely and which are target dependent. Okay, but now I want to look at another problem. I want to include now 3 objectives. And as you already have seen, this approach is the instance we're looked in is very large and so on, but we want to find out more about working with 3 objectives. So we just look at the operation optimization. I leave out the design part, the investment planning for now, just to get something done here. And I want to use this epsilon constraint method, but 2 different kinds of epsilon constraint method. The first one is something, I call for now fixed grid algorithm. At first, I have to choose where I start with my epsilons. Basically, where is this area I want to look at? And we did it the following way that we tried, this point is the utopia point, and this point we got by lexicographic optimization in the 3 directions. First, costs at first, then emissions and efficiency to get one of the coordinates, and then for cost, efficiency, and emissions to get another coordinate. So this way you can get this point. In further approaches, they did not optimize for cost at the first, but only for those 2. So this even makes the space much smaller we want to look at. And we want to make it small to have to really make use of the computational effort that we have to do. And now we divide the grid evenly. We chose the epsilons such that we get this equidistant grid. And for each grid cell, we can solve the problem to get one of the solutions. So we get different distributed solutions evenly. And the second algorithm is that we take again the same area, but now we don't want to have a fixed grid, but generate the grid dynamically. this is we divide it in half. We look where we find a solution, and then look at this area where we found a solution and divide it in half again. And so you can really look in this interesting areas and can get rid of the large areas where you found nothing immediately. There was already an approach where they divided at the solutions. We decided to divide in half, to really get not too tiny in one direction. And now we applied it not to whole Berlin, this was too big. We applied this to a singular district of Berlin, which is somehow a centralized system where most of the heat is generated by one gas plant, and there are some smaller other plants. And we looked at a month, 2 different months, and have a 4-hour time step. This time we have a graph with about less than 200 nodes and edges and about 70,000 variables and constraints. We applied both of the methods I mentioned now, both of the epsilon constraint methods. Algorithm 1 is the fixed grid algorithm. Algorithm 2 is this dynamic grid. And I think for the left month here that we looked at, it's nice to see that here's really this grid visible, and it gives a nice overview of the oval shape of the Pareto front, while the second algorithm dives into this region. And I think for this, in my opinion, in this month, the fixed grid gives you more information than the other algorithm. But for the shape that's giving of the Pareto front for this other month, there the fixed grid, only gives you limited information, but this algorithm 2, the dynamic grid, really finds this, this edge of the region, which we couldn't find without it. So I think both of the algorithms are important, but for different applications. And this is why I try to compare them. If we look at the grid, the fixed grid algorithm has a dynamic grid, and the dynamic grid is, in addition, really dependent on the shape of the feasible space. For the runtime, the grid can be adapted to the runtime needs in the fixed grid algorithm, because you can just use smaller epsilons. And not smaller epsilon, but few epsilons. And for the runtime of the dynamic grid algorithm, this is a minus, because we do not know in advance how much regions are there to discover for this algorithm. The fixed grid algorithm works best in dense feasible space, because when it's dense, we want to have an overview, because in a dense space it could go in all directions with a dynamic algorithm, and the dynamic grid works best on sparse spaces. The coverage is for the fixed grid algorithm, as I said, like an overview of the shape, and for the dynamic grid, more specific solutions in clustered regions. For the fixed grid algorithm, it terminates when we searched all grids. For the dynamic grid algorithm, we already can exclude large regions and then decide what is our criterion to stop this. For example, the size of the grid cells. And the fixed grid algorithm can be parallelized, while the dynamic grid algorithm can only, there's only limited options to parallelize things. And then again, we tried to apply at least one of the algorithms, the fixed grid algorithm, to the whole Berlin instance. This is the same as before. We have a little bit less variables and constraints because there is no investment planning here. And you see here 2 different visualizations of the same result. Maybe it depends on how you can see better what is going on. On the left-hand side, just a plot of the solutions we got as before, and on the right-hand side, you have on the x-axis the CO2 emissions, on the y-axis CHP. and in color the cost. In both of the pictures, you see like there's a huge bulk of solutions that are hanging together in one area. And then there are two that are outliers here, and here's the color. And maybe a decision maker would say, okay, these are too unsure for me. I want to have one solution out of this area where all cluster together. And that the reason that there are these outliers is that we do not put constraints on the costs. And on the right side, I think it's nice to see the grid really that we used for this fixed grid algorithm. Okay, this is what we have done for now. So the conclusion is that I showed you how you could formulate an integrated design and operation optimization problem with mixed integer programming. Then we showed I showed you that we can generate solutions with reasonable trade-offs by this lexicographic optimization with a simple approach, but with some nice outcomes. And we can do operation optimization with 3 objectives as we use this epsilon constraint methods. But, and this is for me a big but, it's not efficient solvable, because some of the solutions, I had one solution which took like over 50 hours to be generated, and you want several solutions. So I wouldn't say this is efficient. That's why I want to make the algorithms, develop them further such that we can accelerate this whole process. And the second part is that we could only solve them under restrictions. I didn't mention this specifically, but at some of the problems we looked at 24-hour time steps, but we have data for 4-hour time steps, and we restricted us, and we even increased the MIP gap a little bit. So not the initial problem. And then we still not managed to solve operation and design optimization together for 3 objectives for the whole data that we have. And this is the goal, and I want to look now how to do this. Thank you for your attention.